Morning, everyone. Welcome to seamless connection switching in Bluetooth LE applications, which is discussed in the next 30 minutes. I will begin to start to introduce myself. My name is Gerhard Wilbold. I'm a software applications engineer in microchip technology. I'm based in Newham, Germany. I have more than 25 years experience in embedded systems, software development, and RF development. Currently, I support our customers with our wireless products, applications, and system solutions. So let's switch to the agenda. We will start with a short introduction. What is seamless connection switching? Therefore, we need some Bluetooth LE basics, very short. What is central? What is peripheral? Then a short look at the stack architecture. The next step, what we will do is we will show applications in the automotive and in the industrial sections. What are the challenges there? What are the benefits? Next, we will switch to the seamless connection switching in detail, which stages are used and which commands we use for this feature. At the end, we will do a summary of the session. And okay, so let's start why we do seamless connection switching. On the left side down, we have a small animation. We have a smartphone which controls 4 devices using BLE, which is widely used. We want to always be connected with the best device. We want to have only one connection to the devices instead of 4 connections in this example. We want to have a stable and uninterrupted connection, so no disconnect and reconnect would not be a solution for that. We want to use the existing hardware, which means we have to implement this feature completely in software. And we have the requirement, or we say we don't want to change the mobile device, so every mobile device should support this feature. So the complete solution is based on the BLE devices. So let's start with the small basics. We have 4 roles defined in Bluetooth. This is advertiser, a peripheral, central, observer, and broadcaster. We have a look here on peripheral. Peripheral, I guess everybody knows, it does the advertising, has the server role, which provides the data. Typically, it's a single connection to the central. Due to the fact that the peripheral device is mostly battery operated, they have a low power consumption than the central. They have limited resources such as memory, processing power, and they have typically a higher latency and a lower throughput than central devices. Then a small summary for the central devices. The central devices initiate the connections with the peripheral devices. It has the client role, which uses the data from the peripherals. It allows typically multiple connections because it has typically also higher resource availability, more processing power, more memory. It does this scanning and connection initiation. It's responsible for the data exchange, and it has a higher power consumption than the peripheral devices. So, a look on the stack architecture, which is divided in 3 components: the applications component, the host component, and the controller component. The applications is the top layer where the user implements his software. The host part contains GAP, GET, Attribute Protocol, Security Manager, L2CAP, and the host part communicates via the host controller interface with the controller part, which contains the lower layers, the PHY, the link layer, direct test mode. This seamless connection switching feature is completely implemented in the controller part. So the host part communicates via the HCI interface with the controller part, and we extended this interface to implement the feature. Next, we will have a look on the application sections. I will describe or explain an automotive solution, and I will explain an industrial solution. Let's start with the automotive part. In the animation on the left side, we have a truck which has 4 peripheral devices which are connected via CAN. And we have a smartphone which controls the truck itself. And we want to have always the best connection. So when we walk around the car, we want to connect it here with node 1, 2, 3, and 4. And typical challenges here in the automotive sector are interference and signal integrity. You have absorption, adjacent channel, and so on. Then another challenge would be the range. You want to have a good signal completely around or inside the car. Then we have challenges about latency and throughput. We want to have a low latency and a high throughput for real-time monitoring and so on. And another challenge is to integrate this into the existing systems, such as compatibility problems and so on. So if you use our seamless connection switching, the benefit or the most benefit is you will have only one connection here instead of 4. You see only one connection, and the mobile phone is always connected, uninterrupted, stable with the car or with the truck here. And further advantages, you are independent from the mobile device, so there is no extra need on this. You can use every mobile device for this feature. Let's have a look on the industrial application. We have here also the animation down on the left side. That could be here, for example, 4 stations, which are, each station is controlled by an operator. The operator has a smartphone, and he has only access to the station if he is in front of the station, and he connects once with one station, and he is connected with all 4 stations at the time. Typical challenges here are you have a limited number of simultaneous connections because every connection needs resources such as memory and processing power. You have a device discovery overhead. You have to connect, disconnect, which needs some time. Latency, context switching, and range. Latency is you need a low latency. Context switching means you switch between central, peripheral, or you switch between different protocols that are a challenge. And you have also a range. You have the stations are widely distributed, and so they have a range issue. And the next challenge would be device identification. You have to manage all these connections. Benefits from the seamless connection switching. You have a reduced downtime and therefore an increased efficiency because you are always connected. You have no disconnect, reconnect. Therefore, the user experience is simplified. It's simply connect and you are ready. You are able to real-time multi-device monitoring for real-time multi-device monitoring because you have a stable, uninterrupted connection. And due to the simpliness, you have improved safety and an improved workflow. So now let's come to the implementation part. We have here the implementation states. We divided this feature in the configuration state with the setup and the initialization. After a connect request, he enters the connection state. This typically normal BLE connection. In this state, we do the connection, and if the connection is complete, we start the synchronization. We have, from the connected node, we distribute the information to the other peripheral devices, and after this synchronization is complete, we will enter the switching mode, which is the main mode of the application, where we can switch seamless between the different peripherals. So here, more detailed look on the configuration state. It's here on the right side. We start the configuration state is the idle or init state. It started after system reset or power on. Then we do the hardware initialization and the systems initialization. Then we check the configuration. If the configuration is valid, we continue. Otherwise, we wait for configuration. if the configuration is valid, we initialize the peripherals. The peripherals are initialized with the same Bluetooth configuration. They have the same advertising data, they have the same advertising parameters, and they have the same Bluetooth LE address. So we have, for example, here 2 identical BLE devices. And then we start the advertising. So at the end of the configuration state, all peripheral devices are advertising with the same parameter set. The central device itself detects only 1 peripheral device instead of n. So if this is done, we wait for connection. You will see here in the diagram, peripheral 1 and peripheral 2 are advertising. The central device is scanning, and then it requests a connection request to peripheral 2. Peripheral 2 is then connected, and the peripheral 1 is still in advertising mode. So then we have the situation at the connection state. The connection is valid between central and peripheral 2. We have 1 peripheral connected, and the other peripheral is still in advertising, and that device needs to be synchronized. So we enter after the initial connection. I have here the sequence charts for the central. Okay, central is scanning and the peripherals are advertising. You see this with the advertising data which are sent. Then the central raises a connection request. It's signalized to the host that the connection is complete. Then we use the handover to command, which reads out the configuration, the connection configuration, and handover 1 distributes the connection to the to the peripheral 1. So peripheral 2 is active connected and peripheral 1 is passive connected. So now we have in the synchronization state the 2 peripherals, and the synchronization is started after connection information is available on all nodes. The synchronization task itself is implemented on the peripherals only, so we have no additional host activity. And when the connection information is available, we start on the passive mode an RX window where we scan for the next connection channel, for the next channel. If we get data from this channel, we are synchronized. The situation is the same. We have it now, all peripherals are connected. One is active connected, which means it gets the data from the central and sends back the response. And the second one, peripheral 1, is passive connected. It also receives the data from the central and with the correct timing, but it does not send any reception back to the central device. So the central device is still only 1 connected device, and the other peripheral devices, 1 peripheral device, is active, and the other one is passive. So if the synchronization is done or completed, we enter the switching state. This is the main state. In this state, the connection is done. The peripheral device gets the RSSI information, each connection interval, and the host controller has now the action to monitor the received signal strength from the peripheral device. He can now decide which one should be active, which has the best connection reception indication, and then he can toggle. Toggle means he has to switch the role of the peripheral device from active to passive and vice versa. This is shown here. We switch the active device to passive and the passive device to active. So in the next slide, I have to show that it's a very optimized command set here. This is switching state in a sequence diagram. The central device sends the data PDUs to the peripheral device. In this case, peripheral 2 is active and sends back the response. Both devices get RSSI value from the connections and distribute this information to the host. The host has then to decide which one should be active, which one should be passive. And he sends the command peripheral 2 to passive and peripheral 1 to active. The role is switched on the peripheral side, which on this side is the synchronization done of the role switching. So, and after that we have the peripheral 1 in active mode and the peripheral 2 in passive mode. The central device doesn't detect any change. It sends continuously his data packets. And now peripheral 1 is responding and peripheral 2 is only listening. So, for this approach, we have a timing constraint for the synchronization phase. The timing constraint is when the connection indication is detected, and we have to read the synchronization or the connection information and distribute the connection information. We have a sync window. The sync window consists typically of the transmit window delay, transmit window offset, and the connection interval. Within this time, we have to provide the information to the nodes, and then we can have a successful synchronization. So let's have a look of the system components we use. We have here on the left side the central device. The central device is typically a smartphone. Is the user interface that monitors and controls the data. And we use in our demo on the booth the microchip Bluetooth development app, which does nothing else as connect, disconnect. Let's come to the peripheral devices. We have a host controller, which has the application component and the host component on his side and does the communication with the peripherals, either via UART, SPI, or CAN. In our demo, we use CAN. And we have 4 wireless controller PICs, 32CXB-Z2, which does the controller layer, controller component of the BLE. So let's come to the summary. Seamless connection switching offers several advantages, making it efficient choice for implementation. The solution is fully Bluetooth based. There is no additional thing. We have only extended the HCI interface by 3 commands. The solution is fully software based. You need no additional hardware. You can reuse your hardware. We have minimal load added on the host controller. You have seen in the previous slides, we only used 3 commands. The rest of the implementation is done on peripheral sides. That's the 3 commands. And we have, due to the seamless connection switching, no communication downtime. So we are always connected. We are always connected with the best one, the nearest one. And yeah, that makes it an efficient solution for seamless connection switching. So now I will come to the end and would say thank you. And if you are interested, please visit us on our booth in Hall 3A, 135. And thanks for your audience.